honor for me to chair today's colloquium, and a great pleasure to introduce our today's speaker, who is Professor Białynicki Birula. Ivo is connected with our faculty for years. In the beginning of his career, he got his master here in 1956. He received also a PhD in 1959 under supervision of Leopold Infeld. So he comes from the Infeld school. However, his personal interest, are slightly away from the interest of Leopold Infeld. He is mostly interested in quantum electrodynamics, in field theory and atomic physics. And of course, he has numerous successes. I will not list them, even I will not dare to list them. But it's enough to mention that for his achievements, he received in 2014, as far as I remember, the most prestigious Polish prize in science, the so-called Polish Nobel Prize of Foundation for Polish Science. And today, Professor Białynicki Birula will tell us a story about uncertainty relations to some figures. Floor is yours.
I'm glad to be here, and I hope that I will tell you something that you don't know, even though Heisenberg uncertainty relations is. So I will tell you something which is rather unexpected, because you may think that Heisenberg uncertainty relation now is such a popular subject. When you write Heisenberg uncertainty relation in Google, you get 600,000 hits. So let me begin on a lighter theme. This is based on a paper that we have recently written with my wife. But just to entertain you a bit, let me tell you why we were interested in this subject. Well, mostly because it's there, like Mount Everest, and poor George Mallory said this famous sentence, why? Because it's there. And Heisenberg uncertainty relation is there, so it's interesting to do something about it. Perhaps there is something more to it. Perhaps one can still discover something, and the reason for this hope is that Heisenberg uncertainty relation in relativistic quantum mechanics is different, as you will see, as I will try to show you. But of course, Heisenberg uncertainty relation now is a trademark of quantum mechanics. It plays the same role as E equals mc squared in relativity. You can buy various t-shirts. There is a program run by University of California in Santa Barbara which offers tours of ecotourism and the Heisenberg uncertainty principle, and the connection is written here. Just as the observation of subatomic particles disturbs the particles, so whale watching disturbs the animals. And here is a picture that University of California puts as an advertisement. You can go on elephants instead of going on cars, so you don't disturb the surroundings. Well, here is another usage of Heisenberg. There was a play that was quite popular in the United States, a play called Heisenberg, the Uncertainty Principle. And the explanation of the author of this play was that Heisenberg principle, simply put, states that humans have an unavoidable tendency to influence situations that they may think they are only observing or have part of it. So using this theme, there was this play. And of course, there are various jokes, like this one. According to the Heisenberg uncertainty principle, a candy bar could jump out of the vending machine if you just wait long enough. And finally, for those who are familiar with the present automotive industry, there is this cartoon, German ingenuity. Who can tell me the name of the concept developed by this German scientist here? Whereby in the act of measuring something, we influence the result. And of course, the crowd says, the Volkswagen principle. Okay, so the first statement about the principle is contained in this paper by Heisenberg. It was written in Copenhagen, that was then the mecca of quantum mechanics at the Bohr Institute. And this was written on the 23rd of March. And this is about the clear content of quantum theoretic content of kinematics and mechanics. And this was just a hand-waving argument that was contained in this paper, and the statement still was quite sound. Je genauer der Ort bestimmt ist, desto ungenauer ist der Impuls bekannt und umgekehrt, which translates, the more precisely the position is determined, the less precisely the momentum is known, and vice versa. And it was just a few months later that Kennard proved, notice, Copenhagen again, in the same institute, and he gave a mathematical derivation of Heisenberg principle using just inequalities from known in mathematics. And this is how now this principle is taught. This is a mathematical inequality. The textbook derivation extended to 3 dimensions. I use the 3-dimensional picture because it's much more important in physics. So one can use Cauchy-Schwarz inequality, or a very simple argument which I will briefly recall. This is high school mathematics. If you have a quadratic form in the variable zeta, then there are 3 possibilities. Either this parabola does not touch the axis, or there is 1 point, or there are 2 roots of this quadratic equation. And of course, here are the conditions that depends on the sign of the discriminant, and the case where the parabola does not touch is 4ac greater than b squared. So now let's apply this simple argument to the following object. We have here something which is obviously non-negative because it's a modulus squared integrated. And when you expand this expression, you find that it can be written as a quadratic form. Zeta squared delta p squared plus 3 zeta h plus delta r squared. This is just this modulus squared of this expression. And the condition that this is never less than 0, the discriminant is never less than 0, gives simply the Heisenberg uncertainty relation in 3 dimensions. You can see it's in 3 dimensions because we have a factor of 3 here. Well, uncertainty relation grew up as a major enterprise. There are various types of uncertainty relations now in usage. I am proud to be one of the founders of the so-called entropic uncertainty relations, and I would like to pay tribute to my friend who prematurely deceased, Jurek Białynicki. We have written the first paper on the entropic uncertainty relations. One can further extend this to other measures of uncertainty, Renyi entropy. However, in this talk, I will stick to the traditional form of the uncertainty relation, and we go to relativistic quantum mechanics now. This is the Dirac equation, we take the Dirac particle described by the 4-component object called the B-spinner, and here is the equation, and alpha and beta are 4x4 Dirac matrices. It would seem at first that we are in business, that everything is as simple as possible, because Dirac said, the square, this is a quote from his book, the square of the modulus of the wave function psi alpha, summed over the 4 components, should give the probability per unit volume of the electron being at a certain place. Well, therefore, I am using here a simplifying convention that the origin of the coordinate system is at the center of this wave, Dirac wave. And here is the definition of delta R squared. It is simply the density, probability density, multiplied by R squared, which is the measure of the dispersion of this wave. And it must be normalized, so it's divided by n squared, as in non-relativistic quantum mechanics. Now, delta p squared, again, is defined in terms of the Fourier transform of this object. Fourier transform is the standard Fourier transform. Of course, the n squared coefficient is the same written in momentum space and in the coordinate space. So we seem to be in business because we can again form the same here combination R. Now I am omitting the average value, assuming that everything is centered. So here we have the same expression, modulus squared is greater than 0. We have the same quadratic form, and we get the uncertainty principle. And now you may expect that we are in business and everything is fine. However, the problem is that this inequality is true. There is no mistake in my mathematics here. However, it can be improved and it should be improved. So why the standard derivation does not work for relativistic particles? Where is this difference? Because we have something that, of course, even Dirac could not disentangle at the beginning, because the solution of the Dirac equation has 2 parts. It has positive energy part and negative energy part. And of course, there was a lot of confusion at the beginning until the proper understanding was reached when the antiparticle was discovered by Anderson. And now we know that the solution of the Dirac equation has 2 pieces. One is genuine wave function of the electron, and the other piece must be treated with some care. And I will not consider this second piece because I am interested in the behavior of the electron. So this electron is only described by 1/2 of psi. And that is an important difference. What is then the free electron wave function? From these 2 pieces, I should take only 1/2 of it. And this is what is written here. I only take the part which has positive energy. The other part does not appear here because it's a free particle. There is no pair creation. I don't have to worry about the second part. And there are 2 functions, 2 amplitudes, one may say, f, which describe the true degrees of freedom. S takes on 2 values, plus and minus, and it is, of course, the degree of freedom of the electron spin. So the inequality that I derived before is true, but the question is this a sharp inequality? Can we reach the limit here? In order to reach this limit, we would have to solve the equation, because this expression here is 0 only if this function under the integral is identically 0. So we go here and we ask the question, can we solve this equation? And the solution of this equation is a simple Gaussian function, and this is how we prove in non-relativistic quantum mechanics that all Gaussian functions are limiting cases where the exact value 3/2 times h is reached. But for the Dirac particle, this does not work because we cannot take the Gaussian, since this would not be representing electron. It would have an admixture of the other part, of the negative energy part. So the mathematical quest now is to find the true minimal value of this expression, considering that we only can vary the true degrees of freedom, not the whole psi, which has 4 components, but only, so to speak, half of these degrees of freedom. So let me make the following definition, that if gamma is just this expression that would stand on the left-hand side of the Heisenberg uncertainty relation, and I will skip the details. I don't want to bore you with the details. The variational procedure will tell me where is the minimum of this expression. And the minimum of this expression is reached when the following equation is satisfied. Luckily, this equation is just a Schrödinger equation in radial variables in 3 dimensions. Here you see the Laplacian at the beginning and then some potential. The potential is quite complicated, though. And I introduce here dimensionless variables. One dimensional variable replaces p. And this variable is p over dmc. And d is an interesting coefficient. It is dimensionless. When you write down dimensionality, you will notice that all dimensions cancel. This is a dimensionless parameter. And this is the crucial parameter because it can be varied and it has physical interpretation. So here we have this equation, and the quest is to solve this equation. Unfortunately, analytic solutions are not possible. At least we couldn't find them in this paper. 2 cases, however, are important. One case is when d is equal to 0. In this case, when d is equal to 0, we are left just with harmonic oscillator, because everything disappears except q squared. So the equation is v of q is q squared. Everybody can solve this equation. The wave function is a Gaussian, and gamma naught is 3/2. This is the non-relativistic case, and I will comment on that in a moment. I consider also the ultra-relativistic case. When d goes to infinity, then again it's a soluble case. In addition to the harmonic oscillator in the potential, we have a unit strength of the repulsion 1 over q squared, typical centrifugal force repulsion. And the wave function f is given by this formula. And remember this formula here. Gamma for ultra-relativistic particles is given by 3/2 augmented by the square root of 4/5 and 9. So here is a picture of the curve lines of the potential. We have d equals 0, which is harmonic oscillator. Then we have d equals infinity. And in between, we have various cases. And as we go from d equals 0, the barrier is higher and higher. And we can find values of gamma that correspond. They are given here in proper scale. The lowest value is the ground state, speak, d equals 0, and then when we increase d. Now, what is the interpretation of this d, which makes the whole difference here between relativistic case and non-relativistic case? Well, in relativistic theory, we have a scale. There's no scale, preferred scale, in non-relativistic physics because there are not enough constants there to build such a scale. But now we have the speed of light, and the presence of the speed of light makes it possible to combine the expression here into a dimensionless object. And now this dimensionless object is telling us something about the nature of this solution. When d is much less than 1, we have non-relativistic wave packets. Look, what does it mean that d is much less than 1? D is, in these units, the ratio of the Compton wavelength to the expression written here. So when d is much less than 1, we have the wave packet, which is large as compared to Compton wavelength. When you have such an extended wave packet, then of course the momenta which are present in building this wave packet are small, relatively small. When you squeeze this wave packet, then you make the momenta higher, and this takes you to the relativistic regime. If momenta are small as compared to the scale here, then you have relativistic versus non-relativistic. Now, to make it even more interesting, we have also studied the Heisenberg uncertainty relation for photons, and you will see at the end an interesting connection between electron and the photon. Now, there is a problem with photons. Why there is a problem? Because there is no position operator for the photon. You cannot just multiply the wave function of the photon by r and have something sensible. So we need a completely new approach, new definition of the uncertainty relation for photons. Fortunately, photons are relativistic particles. And for relativistic particles, we have the whole special theory of relativity that we can use to help us to find the proper operator for the position. So among the operators that act as generators of various transformations in relativity, we have something which is called the boost sometimes. And for those who don't remember this, I gave this correspondence. Angular momentum is y pz, the x component, minus z py. These are rotations in yz plane. Now we can introduce the analogs of these rotations, but they are rotations in xt, yt, and zt plane. And generators, these are generators of Lorentz transformations that take you from one coordinate system to a moving coordinate system. Now, as you see, these generators nx and y and z have a piece when you put time equal to 0, when you study this at t equals 0, then it is simply the position x, y, z divided by the energy. So that is the reason why here we have this combination. You cannot just divide by the energy, because for operators that would not give a Hermitian operator as we would like to have in quantum mechanics, but we can divide by square roots on both sides, which will give us a good center of energy operator. Why is it a center of energy? Because of this connection with the generators of the Lorentz group. And now we have the same problem. I will not go through this calculation. It's rather awesome because you get a complicated variational principle what I want to show you is this final result. The final result is ultra-relativistic electrons have the same bound on the right-hand side as photons, which makes sense, of course, because if something is moving with the speed, almost the speed of light, then there should be similarity between all particles that are moving close to the speed of light. And as I have shown before, it's exactly the same result that is obtained for electrons. One must, of course, admit here that these are limiting cases. Non-relativistic wave function is not obtained for some value of d. You must go to the limit, put d equals 0. The same for d going to infinity. Only in the limit you get this nice result. So in summary, my conclusion is that first, there's big surprise. We really were surprised that 90 years have passed and no one asked a simple question. Are Heisenberg uncertainty relations valid in the same form as in non-relativistic physics? They are not. And of course, now there's some hope, perhaps, that when we go deeper and see the difference, then perhaps there is something more about physics of relativistic particles that can be discovered. And this is why the title of my colloquium here is "The Saga Continues." I hope that it will still continue and there will be some interesting conclusion that can be reached. Thank you very much.
Thank you very much. And the talk is open for discussion. Questions or comments are welcome.
So I've heard a story about Heisenberg talking to Bohr about his interpretation of uncertainty relations, the one that you gave. And the story is that Bohr told off Heisenberg big time, so that Heisenberg left the discussion with tears in his eyes. Bohr simply told him that there is this interpretation where you explain that you cannot measure an electron or any particle without disturbing it. It has nothing to do with the spirit of principle of uncertainty. So why do you keep going? I mean, why do you still, do you have a reason to use this interpretation to the inequalities that you give?
Well, my position is quite simple. I am doing a well-defined mathematical calculation, and this mathematical calculation, regardless of the interpretation, which of course anybody can have his or her own interpretation, will be correct if it agrees with mathematics. Mathematics is telling me if I define the uncertainty in position in a certain way, which seems to be sensible, and the uncertainty in momentum in a similar way, then the product of these measured properties has a lower bound. That's it. I don't have to worry about the interpretation going much deeper, because as we know, the interpretation of quantum mechanics has many, many possible approaches. And in this particular case, interpretation, in my opinion, does not matter. The formulas are correct, and the rest is in the eyes of the beholder.
I would like to ask you what would be about antiparticle creation, because in this case we have to do not with one particle but with three. For example, in the simple case with an electron. Well, if you have sufficient amount of energy, uncertainty in energy, you could have some kind of antiparticle creation. And all of this interpretation, all of this calculation could be in some sense, obsolete because you have no one particle but free.
Again, let me stress that this is for free electrons. And free electrons are well-defined objects. They satisfy the Dirac equation and the requirement that they have positive energy. Such a wave function is uniquely defined. It has 2 degrees of freedom, so to speak, because the electron has spin. And I'm not talking about electrons. However, in our paper, we also calculated the uncertain relation for the electron bound in an atom. And then you can do the same calculation. As we all know, in a hydrogen atom, there are positive energy states and there are negative energy states. Negative energy states correspond to not to electrons, but to positrons. So when I restrict the solutions of the Dirac equation only to positive energies, then the same argument goes and one can calculate the uncertainty relation.
Yes, but you have also an electromagnetic field because
I said this is for free electrons. For free electrons, there is no, by definition, there is no electromagnetic field. I'm not trying to write the uncertainty principle for something much more complicated, which becomes totally untractable if you take the interaction of the particles into account. Then, of course, many things can happen.
Other questions or comments?
Did you try to solve the differential equations numerically to get the intermediate value of force?
Oh yes, that was found numerically. These values were found numerically. By a simple shooting method, you shoot and you see whether your wave function dies down. If it doesn't, then you slightly change the value of the initial and then of the energy, and then you find the value of the energy by numerical methods.
Thank you.
Other questions or comments? Coming back to the atom, I mean, you said that you did some investigation on the hydrogen atom,
yes,
but
yes.
only for the ground state or also for excited states? How the centrifugal force will...
For the ground states, because we were bored by the complexity of the wave function, but because in this case, one would like to do the calculations analytically, of course. And for the ground states, it's something that is simply analytically possible.
And are there any consequences for the binding energy of
No.
Nothing like that.
This is just a certain view that you can associate with the state to see how the spread in momentum is connected with the spread in position. But I don't think it has any value as a tool to discover some other properties of the hydrogen atom.
Okay, if there is no more question, let us thank again Professor Białynicki for